Okay, this is another problem, like the ones we've been working to try to find shear force and bending moment. This problem does have a slight advantage in that you'll notice that the loading is continuous across the whole structure, so we should be able to write one set of equations that are good for the entire structure. If we're going to cut it here, as I've indicated at X, and again we're looking at the left or the right-hand side, does either one of those offer us any advantage, or is one have a disadvantage? And from my perspective, the answer is no. Both sides require that you find some reactions. That's pretty equal. Both sides are trapezoidal loads, pretty much a wash. But this left-hand side will be all in terms of X, which will be easier to manage in your equations than the right-hand side, which would be in terms of 18 minus X. And although that's not hard to deal with, it's just more stuff to drag around and make your equations a little harder. So I'm going to say that the left would be the best way to go. And with that said, I'm only really interested in finding my reactions at A. So let's start by doing a free question. Okay, let's start by doing a free body diagram of the whole structure. And I'm going to put my positive shear at A. And just to show you, this would be positive shear at B. Okay? Those are both positive shear forces as drawn. We're not going to worry about B, but I thought I'd put it there anyway. The next thing we want to do is I'll first consider just the rectangular portion of the load. So if I do that, it has a unit of 1 kip per foot. So what would be the concentrated equivalent force for just the rectangular portion? Something like 18 maybe. Yeah, because it's 18 times 1, so it would be, in Mr. Copeland's words, something like 18 maybe. Which is an interesting way of saying things. Maybe you're right. Maybe. I think you are. And then what's the distance? We're going to try to find the stuff at A, so I'm going to be doing my moments about B. So what's the distance from B? Half the distance, yeah, would be 9 feet. Now, what about the triangular portion of the load? Now, if this part is 1 kip per foot, that means this part over here is also 1 kip per foot. So what does that leave for the height of the triangle? 2. This is a classic mistake when you're under stress in the test. You run over here and you say the height of the triangle is 3. But it's not. Make sure you subtract out the rectangular component. So I have a question. I saw a hand go up.
That's fine.
Okay. So now we want to find the concentrated equivalent force for that, which would be 1/2 base times height, which is surprisingly what, Mr. Copeland?
Something like 18 maybe.
Something like 18 maybe. And what's the distance from B? 1/3 the distance. 1/3 of 18 is 6. So with that set up, we can now sum moments about point B. Make sure it's in equilibrium. Both these 18 kip forces are going to create what kind of moment about B? Positive. The first one have a moment arm of 6 feet. The second one have a moment arm of 9 feet. And then I'll have my reaction, which creates negative moment at 18 feet. So the shear at A should be 9 and 12. What is it? 9 and 6. It should be 15. Is that what you guys get? And it came out positive, so I did assume the right. It is positive shear. Okay, so let's go down here and draw the free body diagram. for our structure. I'm going to draw this a little large so we can see all the components. So we'll cut it at a distance x. We'll have a positive shear force at A of 15 kips. I'm going to assume positive shear and moment at the cut. And then I'm going to have a load that starts at 1 kip per foot and goes to some value, and it will be trapezoidal. What is that value? What is the load as a function of x? We talked about this before, so it's a straight line, so what would be the y-intercept? What would be the constant value? When x is equal to 0, what's the load? 1. What's the slope of the line? It would be rise over run, so the rise is 3 minus 1 or 2, and it would be 2 over 18, so that's really 1/9. So you should get x over 9 plus 1. So when x is 0, you get 1. When x is 18, you get 3. Everybody see that? So it does match.
So that's basically just the equation of that line.
That is the equation of that line. Now when I break this up into a rectangular and triangular piece, I'm going to run out of room here, so I'm just going to call the rectangular piece force 1 and the triangular piece force 2. What's the distance to F1 for the rectangular piece? X over 2. And what about the distance to F2, the triangular piece? Be x over 3. So what is F1? It's just x. That wasn't so bad, was it? Base times height. What is F2? Well, it's a triangle, so it's going to be 1/2 base. Base is x. So what's the height of the triangle here? Well, the total height is x over 9 plus 1, but we're going to subtract off 1. So you should just get x over 9. Everybody see that? You can check that too, because when x goes to 0, what's the height of the triangle approach? 0. So when x goes all the way to 18, what's the height of our triangle? We figured it out here. It was 2. So you put 18 in there, you get 2. So it seems to match. And when you do all that calculation, you get x squared over, surprisingly, 18 keeps popping up a lot. I don't know what that means. Probably nothing. Coincidence. Now I'm ready to go. So now I can sum the moments at our cut section, make sure they're in equilibrium. Right-hand rule for my sign convention. So starting here, that's a positive moment. F1 and F2, what create positive or negative moment about the cut? Positive. So I'll start with F1, which is x times a moment arm of x over 2, plus F2, which is x squared over 18 times a moment arm of x over 3. And then I'm back to my reaction, which creates negative and has a moment arm of x. So just in case you lose track, this was F1 and its distance. This was F2 and its distance. All right, now we got to put all this together. So what is the moment as a function of x? I'll start with the largest term first. So this looks like, to me, x cubed over 54. And that would be minus x cubed over 54. And then we've got this term here, which will be minus x squared over 2, and then plus 15x. Do we know something about the moment in this problem? What's the moment at A? It's a pin.
There is no moment.
Thank you. So that would be numerically? 0. So that means the moment at x equals 0 should be 0, is it? Yes. What about at B?
0.
Should be 0. So the moment at x equal 18 should be 0. That may take you a little longer to do. Somebody plug that in and see if that's also 0. I have a feeling it will be.
Me too.
But while that's happening, let's go ahead and calculate our shear by summing the forces in the y direction. So our shear force is acting down here. Also, F1 and F2 are down, so that's minus x squared over 18. And then our reaction force is acting up. So when I solve for the shear as a function of x, I'm going to rewrite these in terms of the power. And again, the units should be kips. Oh, I left off my units up here, sorry. This should be in kip feet. Anybody check get this? It's okay? Excellent. So there's our shear equation. Now what can we use to make sure, to hopefully make sure that that's correct? Let's do the quick one. If you take the derivative of the moment with respect to x, do you get the shear? I say yes. So that's a good sign. We also know the shear. What is the shear at x equals 0? We solved for it, right? It was positive 15. So you put in x equals 0 here and you get 15. So that's pretty good. Now we don't know the shear at B because we didn't compute it. But I think the shear at B is 21. Just doing a quick up here. And I think if you check that the shear at x equal 18 is equal to what? I think you're going to find it's negative, what did I say? 21, is that right? Yeah, I think you'll find it's negative 21. So why is it negative 21? Because positive shear at B is down, but when you solve for this, you'll find that it's actually up. So you have positive shear force at A and negative shear force at B. And I think that matches our equation when you put in x equal 18. Any questions about this one? Again, this is a very testable problem for the exam. No questions?